Welcome, everyone. I'm David Bader, and I direct the Institute for Data Science at the New Jersey Institute of Technology. I'm pleased to welcome Jon Kleinberg, our speaker today, who will be talking about fairness and bias in algorithmic decision-making. It's a very timely topic. Dr. Jon Kleinberg is the Tisch University professor in the Computer Science Department at Cornell University. His research focuses on issues at the interface of networks and information, with an emphasis on the social and information networks that underpin the web and other online media. He's a member of the National Academy of Sciences, the National Academy of Engineering, and the American Academy of Arts and Sciences, and he serves on the SCI's Advisory Committee of the National Science Foundation and the Computer Science and Telecommunications Board of the National Research Council. He's a recipient of the MacArthur, Packard, and Sloan Foundation Fellowships, as well as awards including the Rolf Nevenlina Prize from the International Mathematical Union and the Frederick W. Lanchester Prize from Informs, as well as the ACM Infosys Foundation Award in Computing Sciences. Thank you, Jon, very much for agreeing to speak. And I'll turn the screen over to you.
Okay, well, thanks very much for the invitation to take part in this seminar series, and it's a pleasure to get to talk here remotely today. And so what I want to talk about was something that is really, I think, an issue that we're increasingly encountering in data science, AI, algorithms, machine learning, this constellation of areas, which is thinking about some of the societal implications of the way that data-intensive systems are being deployed to make consequential decisions in many domains that we think of as traditionally offline domains. To think about the societal design implications, right? The impacts it has on how we might think about building these systems. This is it's a highly interdisciplinary area, and in keeping with that, the work I'll be talking about is joint with my Ph.D. student, Manish Raghavan, and three faculty from three different research areas: Jens Ludwig from public policy, Sendhil Mullainathan from behavioral economics, and Cass Sunstein, who's a professor of law. And this research, of course, also comes at a time, that obviously, many of us are experiencing profound disruption in our lives. We see a lot of anxieties. We see a lot of pain being felt by a lot of people, I think, in being born unequally by different groups of people. And I think it's natural in those situations to ask what we as, technical people can, do to try helping with these problems, and to think about how our own actions, might be impacting things for better or for worse. And in order to sort of set that context, it's actually, useful to go back to the ways in which the systems that we built, beginning in, especially the late 80s and all through the 1990s, began to have this social dimension to them, right? So it's a fact that we've now been familiar with for 20 years or so in computer science, that the systems, the large platforms that we're building, have both a social and a technical component. This idea that we are truly building according to these two different axes, an idea that had been sort of pervasive in areas like human-computer interaction since its inception, that really became mainstream in computing over the past 20 years, right? That we're building these socio-technical systems. And I think, speaking for myself, but I think for a lot of people, who I've worked with in this space, a lot of the building of these systems over these 2 decades was really came with a kind of long-range sense of optimism that by truly taking into account, not just the technical factors, but also the social, behavioral, and economic aspects, that we would be able to build things that would, do good things for the world. But of course, as all of us have experienced over the past 6 to 8 years, these systems have rebounded, against some of our efforts at design in unexpected ways, right? They're we see them, generating conflict and polarization. They carry misinformation. They make decisions about people that can be unfair to certain groups. And so it's almost as though there's this as we move around in this rich two-dimensional world, there's almost like there's a third dimension that's impinging on us. And I think one way to understand this this recent activity in research on topics like fairness and bias is to appreciate that this third dimension has been starting to come into focus, right? There really is this normative dimension to what we build that's independent of the social and the technical, right? This notion of, in plain language, what is the right thing to do? What is the desired outcome from the systems that we build? What is good for society? And to appreciate that that's really a distinct question from the idea that we're building socio-technical systems, right? That just because an actor deeply understands the social dimensions of the platform they're building doesn't mean they will necessarily use it for good purposes, right? That is a distinct question. And I think that's a question that technical communities have increasingly been engaging with over these past several years, right? This is, of course, incredibly challenging, right? Realizing that there's this additional dimension that we have to think about doesn't in any sense correspond to knowing what to do about it. But I think it puts the question on the agenda for the research community in a way that it hadn't been nearly as salient before then. And that's an important development. The particular set of questions in the space that I wanted to talk about were these settings in which we begin using algorithmic classification for problems that we've traditionally thought of as offline problems, and to ask about some of the implications for bias and decision-making in those settings. And in a sense, this begins from the socio-technical angle, right? Over the past 20 years, we've gotten very good at building online systems for things like ranking and recommendation, right? So this screenshot of a Netflix help page is a good example where, a system like Netflix takes, a user like you, it takes this rich collection of tastes and preferences that you have, reduces it to a feature vector, passes it through an algorithm, and makes some kind of a prediction, right? That there's either a high or low probability that you will like a particular movie, like this movie here. Something that we're very good at doing, following a machine learning pipeline that we're very familiar with. And what's been happening over the past decade is that people began asking, if we're very good at making predictions in the online domain from data, and if many of the problems that we see in the offline world have a kind of prediction flavor to them, should we be trying to make deeper use of data science or machine learning techniques in those settings? So take hiring, for example. There's some power in the idea of abstraction across domains. And if we abstract from ranking and recommendation to hiring, we notice some similarities, that there's a person applying for a job and they have some rich past employment and life experience leading up to this moment. We reduce that to a tabular feature representation of their resume. It gets sent to a decision-making entity. In this case, it's a human hiring committee. And they evaluate it to make a prediction about something, right? Now, here is where the story gets a bit vague, right? We see there's an analogy, but the analogy doesn't feel perfect because it's very hard to say what a human hiring committee is actually doing when it reads a resume. Many of you listening to this haven't been involved in hiring in some capacity. And if you have to write down your objective function in hiring, the way an algorithm can specify its objective function, it would be challenging. Nonetheless, it feels like there's a similarity. And so that tension between the similarities and contrasts is something that I want to sort of explore. Same with college applications. We take someone's K through 12 experience, turn it into a feature vector. It gets read by a human hiring committee, a human admissions committee in this case. And again, the objective function is not entirely clear. So screening decisions. We take applicants, we turn them into feature vectors, and we make some kind of a decision, a high probability, low probability decision, a yes, no decision. We do that when we decide what content to show you online, but we also do it for things like hiring, school admissions, credit, even in the criminal justice domain where data analytic tools get used for things like the prediction of recidivism or arrest for a future reoffense. And of course, the fact that we can deploy these solutions is separate from the question of whether, as a society, we feel they're, making things better or worse. And so in these particular contexts, one question that has come up and has become this very active research area is the risks of bias from the introduction of data-intensive tools into these domains. And many communities have begun both documenting cases where the use of data science tools or machine learning tools has led to instances of bias that we can document, and also the question about what this implies for design. Now, if we want to think about algorithmic bias and what that might even mean, we should start with human bias, because in the beginning, these decisions were all being made by human beings, and over a number of decades, a long line of research in the social and behavioral sciences has been developing increasingly refined empirical understanding of the ways in which human bias, both implicitly and explicitly, manifests itself against certain groups in decision making. Just to give a sort of example of what some of that literature looks like, there were a number of very powerful empirical studies in the 1990s, for example, that have over time attracted a lot of follow-up work, a lot of replication. These are unfortunately quite robust findings, and what they show is that we often have these systematic disparities in our screening type evaluations across different groups. So, just to make this concrete, in a particular example, a paper from Nature in 1997 by two European social scientists, Christine van der Vos and Agnes Vold. What they did was they got data on evaluations of European Research Commission grant proposals. And so as part of the evaluation of the proposal, one of the things that the reviewer had to do was assign a so-called competence score to the principal investigator, right? How competent is this person to perform the research? And so, this competence score is here on the y-axis. What the two researchers, van der Vos and Vold, did was they tried to think of external measures of impact, right, of scholarly achievement that these principal investigators had. So number of papers in high-profile venues, number of citations of those papers, number of past grants awarded, research output on those grants, all of these things. And essentially, no matter how they tried to organize, these measures of external impact on the x-axis, they found that for similar measures of impact, principal investigators who were men were receiving systematically higher competence scores from the reviewers than principal investigators who were women. And research of this type, which established these kinds of disparities in many contexts, falls under the heading of implicit bias research. That, in most cases, we're not saying that there was a kind of deliberate, coordinated attempt to assign systematically different scores, right? This is an emergent phenomenon by hundreds of reviewers over many years, aggregated all together. What we're seeing is that there's a latent tendency, whether we're aware of it or not, to assign scores in such a way that for a fixed notion of external impact, we're assigning quite different competence scores. And again, there's a long history of replication where increasingly we try controlling for the similarity of the people and showing that there's nonetheless a difference. Okay, now let's talk about algorithms, right? Because the interesting contrast here is that algorithms, in contrast to humans, have no direct incentive to engage in bias. The algorithm, after all, has no idea what any of these features actually mean, what the objective function means. It's simply trying to minimize some loss function on held out data, given the training data that it has. Despite this, there are many sources of potential bias in algorithms, and we can sort of quickly see some of the ways in which bias may be making its way into these algorithmic decisions. To take a simple example, suppose I'm trying to train a model to assist me in assigning, in evaluating European Research Commission grant proposals, as human beings were on the previous slide. And so I give it all of the features that I had previously. Those features might include the competence score. And so the algorithm takes the competence score as one of its features. And that competence score, as we saw, is sort of infected with the bias that the human decision-making actually had, right? And so in effect, it's going to be carrying that forward. And it's interesting because we could say, well, we're literally just using the administrative data from this grant program, and we're just putting the administrative data. We're not using any human judgment, but the administrative data itself has completely subjective human judgments recorded in it. That's the nature of past evaluations. We have a similar problem in the choice of objective function, right? If over here on the right-hand side, the question, what is the target I'm predicting? You could easily imagine I get into a situation where the thing I'm trying to predict is effectively a competence score for a researcher. I give the algorithm labels from past competence score determinations made by humans. And again, now I'm teaching it to reproduce the bias that was there on the y-axis of the previous plot. So all of these are reasons why bias might make its way into the algorithm. Now, there's an interesting challenge here that if we want to try auditing algorithms for bias, we run into the problem that algorithms are very hard to interpret, right? So there's an interpretability problem for algorithms. Algorithms trained on massive amounts of data using complex models tend to be these black boxes where it's hard to figure out really how they're making the decisions that they're making. How then are we supposed to look at them and figure out if they're engaging in bias? I wanted to start, though, and this is sort of where my work with Jens, Sendhil, and Cass began, with some context for this, because human decisions in their own way are also uninterpretable. And much of the legal framework around bias and discrimination implicitly recognizes the inherent inscrutability of human decision-making. And so what I want to talk about here was first some of the legal framework around this, some of the ways it relates to behavioral science and the inscrutability of human decision-making. Then come back to bring algorithms into the picture and ask what can happen if we are able to audit the machine learning pipeline. And then at that point, in the second half of the talk, I'll bring some technical models into this. I'll try sort of describing a simple model of what the machine learning pipeline looks like, what auditing of it might look like, and some of the subtle ways in which interpretability interacts with bias. Okay, but let's start with the inscrutability of human decision making, because if I look at the legal frameworks around discrimination, they inherently recognize the fact that we can't know why people make decisions, right? It begins with the fact that the law recognizes two categories of discrimination: disparate treatment, in which I deliberately favor, say, applicants to a job, to stick with our running example. I deliberately favor them based on protected attributes such as race, gender, national origin, religion, or age. But there's a second kind of discrimination, which in the US legal system is termed disparate impact, which says, regardless of the decision maker's intent, if a screening decision has disproportionate adverse effect on a protected group, then the burden of proof shifts to the decision maker to establish so-called business necessity for their decision, right? So a disproportionate impact is not always going to lead to a successful legal challenge, but it puts the burden of proof on the decision maker, right? So for example, if I have a job where people are constantly having to reach objects that are extremely high off the ground, I might say, I need tall people for this job. And there may be, that would have to be litigated, but there may be business necessity for hiring tall people, even if it has a disproportionate adverse effect by gender, for example. On the other hand, if I'm hiring software engineers and I have a minimum height requirement, it would be very hard to justify a business necessity for that. And therefore, the disproportionate adverse effect would be much more challengeable. The problem, of course, is it can be very hard to tell if a human decision maker has engaged in disparate treatment or if they have business necessity for their decisions, because it's very hard to know why people have made the decisions that they made. One simple reason is that the people might be lying. They might just tell you a false reason for why they made the decision. But a deeper and sort of, in a way, kind of more pervasive reason is that they might genuinely not know their rationale for the decisions that they've made. Right. Again, think about your own experience engaging in some screening decision, like hiring. You see three candidates. You really like one of them. You can attempt to articulate your criteria, but it's very hard to know what the real reason was why you made this decision. Now, there's a long history in the behavioral sciences of some very, very creative experiments that establish sort of much more conclusively than these sort of qualitative arguments that people you can sort of establish that people genuinely are not giving the correct reason for their decisions. And these experiments have the flavor of, I create an environment, I bring group A into the environment, I ask them to make a decision. I then subtly change one little thing in the environment and I bring in group B. Group B in aggregate makes different decisions. But when I ask everyone from groups A and B why they made decisions, no one mentions the one thing that I changed between the two environments, suggesting that not only was it invisible to them, but they're happy to invent other reasons that have nothing to do with it. Here's an example. Say I bring people into a lab, and this is an experiment from Nisbett and Wilson in the 1970s. Bring people into a lab and I ask them to engage in a word memorization task. I give them a bunch of words to remember and they recite them back. At the end of that, I ask a kind of non sequitur question out of left field. I say, name a brand of laundry detergent, and they name something. Now, group B, I ask them the same word memorization task, okay? But the words I ask them to memorize are words like beach, ocean, moon, waves. I then ask them to name a brand of laundry detergent. Many more of people in group B say Tide. That's a phenomenon that, that we understand, that's priming. If I tell you a bunch of words in the vicinity of a particular word X, and then I ask you to name a word, you're likely to come out with X. But Nisbett and Wilson did something very creative beyond just priming people. They asked people, why did you pick that brand of laundry detergent? And in both groups A and B, people said it's because it's the one we use at home. It's the one we used when I was growing up. I see it in the store. I recognize the logo. But people didn't say it's because you primed me with a lot of words that involved beaches and oceans, and therefore I said Tide, right? So In aggregate, we know that many people in group B must have said it in part because of the priming effect, because there was a giant statistical difference, but no one's giving that as their reason. So there are many Nisbet-Wilson experiments. I ask people to select clothes off a rack. I orient the rack so that many people choose the rightmost one. But people explain their reasoning having to do nothing with position, but everything to do with color and style and so forth. And so many cases where the experimenter kind of knows that there was something going on, the person. And so what's interesting is this kind of turns on its head our traditional notions of interpretability, right? We often obsess about how algorithms are uninterpretable. And there certainly is a lot to worry about there. I mean, they are very hard to interpret. But we should think about that there are ways in which humans are equally uninterpretable, just in different ways, right? Different ways because a human being typically is always happy to offer you an explanation, but sometimes it's just the illusion of an explanation, right? They're giving you reasons. The hard part is knowing, are these the actual reasons for their decision? This contrast between algorithmic inscrutability and human inscrutability, right? They're both inscrutable, but in such different ways that you start to ask, maybe there are things we can do with algorithms that we can't do with humans in the domain of discrimination and bias. And the argument that Jens, Sendhil, Cass, and I were making in our work is that well-regulated algorithms may actually be able to make discrimination easier to detect, right? Separately from the question of, are they making discrimination greater or less? Let's simply ask about the detection problem, right? Because in the end, establishing a claim of discrimination involves knowing that it occurred and attributing it to someone. Why might they make discrimination easier to detect? Well, so a few things I should make clear. First of all, when we say algorithms, we all know that from machine learning, there are really two algorithms, right? There's a training algorithm. The training algorithm takes training data, it runs for a while, and then it produces as output a classifier, a screening rule. The classifier takes instances and actually classifies them, right? So the training algorithm is an algorithm that as output produces algorithms, classifiers, and then the classifier actually takes the instances. And well-regulated, let's also talk about that. What I mean here is that we're imagining a system in which some regulatory body, some government actor, has compelled people engaging in screening to actually make their machine learning pipeline available for inspection, right? To say, here is the training data that I used with features, here is the algorithm that I used, here's the objective function I was optimizing, right? So that we can go in and actually examine those pieces. Without that, everything I'm about to say, of course, just is, wouldn't necessarily be relevant, right? Because then we just have bad actors using secret tools that we can't inspect. But if I can inspect the algorithm, I can do a bunch of things, right? I can't necessarily read the code and expect to understand it, right? That's something we all understand from the design of software, that just reading code is not usually the answer. But what I can do is I can ask what features were actually used in this, right? What are the relevant features? What objective function was being optimized, right? These are questions I can't ask in any meaningful way a human being, right? I can't go to a hiring committee that I feel is producing a disparate impact in its decisions and ask, what is your objective function? Again, they might be happy to have that conversation with me. They might even be happy to introspect on their own reasoning, but the chance that they're going to arrive at any sort of reasonable model of how they're actually making decisions is extremely low. But I can do all those things with the algorithm. Similarly, I can build my own screening rule from the data, right? So, in the Netflix prize competition, Netflix did not say, please read our code and improve on it. They said, here's training data and held out labels. Can you do better than we did, right? And so if I believe that a decision maker is engaging in bias and they claim business necessity, if I, for example, challenge that by producing a screening rule that has equal efficiency from their point of view, equal accuracy from their point of view, and less of a disproportionate adverse impact, then I've somehow undercut their claim of business necessity. I can do things like probe their screening rule with synthetic instances. I can create, millions of applicants who never existed, run them through the classifier, a kind of counterfactual exercise that I, again, could never realistically do with a human hiring committee. All of this, of course, involves enormous record-keeping requirements, right? This is saying that this is imagining a world that does not currently exist, where we ask people to preserve the machine learning pipeline that they use to build these things. You might say that seems technically extremely onerous, and it is. But the important point is that, in other contexts, when society has deemed a certain kind of decision sufficiently consequential, the law has often imposed enormous record-keeping requirements. Take the regulation of financial markets, for example. Right? Trillions of dollars are transacted in financial markets, and every one of those transactions is recorded in a way that's available to inspectors, right? That's an enormous technical challenge. It involves the expenditure of an enormous amount of resources by firms that would much rather be spending those resources on other things. Nevertheless, we require it. Why? Because somewhere in the policy process, society has decided that the danger of misbehavior or recklessness in financial markets is so high that it is worth imposing that burden on the market. That's a decision that we could choose either to make or not make in these domains where algorithms are being deployed for screening decisions. But the important thing to remember is it really is ultimately a policy decision informed by what's technically feasible. So with that as context, I want to talk about, at the level of building some models, what we might be able to do if we can actually audit the machine learning pipeline. And so let me start with a very simple model for the screening decision, and then how machine learning might make its way into this. So basic ingredients of the decision. So I have individuals who are applying, and again, think about hiring if you want. Each individual has some true feature vector X. Think of this as a very, very long vector consisting of things I might not even be able to hope to measure, but it contains everything relevant for the employment decision. There's also some productivity function, right? If I knew everything about this applicant, how productive would they be if I hired them? Okay, I'm concerned about disparate impact, so I'd like to talk about the difference between an advantage group and a disadvantage group. Advantage group A, disadvantage group D. Now, if I know X, I know everything I need to know, and I don't care about group membership. So in what sense is group D disadvantaged? It's that the relative abundance of feature vectors differs between the two groups. And group A is more abundant in feature vectors that confer higher levels of productivity, right? So people from group A, if they grew up in neighborhoods with more affluent school systems, for example, those people may have gotten more preparation for the job, right? That allowed them to acquire feature vectors X that led to higher productivity. Once an individual has that feature vector X, it doesn't matter what group they belong to. But in one group, it's much more costly to acquire it. So I have an average value of F across the two groups, and it's a weighted sum of these F values. And that weighted sum could turn out differently, even though the constituents, the F of X's, are the same. That leads to a difference in the averages, which I'll call D of F. Right? So D of F is the difference in the average value in group A, average value in group D. Now, D of F is something that in the social sciences you might call structural disadvantage. It's the disparity between the two groups that existed before my decision-making ever arrived on the scene, right? So before we ever deployed an algorithm to evaluate anybody, there was already structural disadvantage D of F that might be greater than 0. We could ask that our algorithm, not make the structural disadvantage worse, the disparity worse. We might also ask that our algorithm reduce it. We might say a goal of our algorithm is to reduce the disparity between groups. Those would all be good goals. But it's important to remember that this disparity exists before the algorithm ever arrived. Now, because the machine learning pipeline is going to morph these functions, right? It's going to start with F and begin training new functions. It's useful to have this D notation on any function. So for any function V, we'll say D of V is the difference between the weighted average in group A and the weighted average in group D. Okay, so what happens when we start deploying machine learning? I would say the machine learning pipeline in schematic form involves the following cascade of steps, starting with feature vectors X, productivity function F. First, the algorithm designer typically does not have access to the true function F, right? It's inherently unknowable. It's how well this person would do in the future, but we approximate it with some other function G. Similarly, the full vector X is also unknowable. It contains many more things than we could possibly measure. So we're going to use a reduced representation, R of X. Now, there's a syntactic issue, which is G is applied to long vectors X. Now I have a short vector R of X. So I apply some other function H. So I'm really saying H composed with R applied to X. First apply R, then apply H. Finally, there's training, right? Machine learning works on a finite amount of training data. So it produces a trained rule T that's designed to approximate the ideal rule H. So after this cascade of steps from F to G, from X to R of X, to H to T, I now have T composed with R as the output of my machine learning algorithm. So we have this disparity. We started with structural disadvantage D of F before the algorithm ever arrived. Because of the algorithm, we now have a disparity D of T composed with R, right? And we could ask, is that disparity bigger, smaller, or the same? And all of those are possible. But what's interesting about this representation is that not that it tells you whether this number is bigger than that number, whether the number on the right is bigger than the number on the left, but rather that it allows you to decompose that number, D of T composed with R, into the constituent parts that we've been talking about, right? And I can do that by simply writing D of T composed with R in this deliberately expansive form, right? It's D of F plus D of G minus D of F plus D of H composed with R minus D of G plus D of T composed with R minus D of H composed with R. right? And everything just cancels out, and I'm left with d of t composed with r. It's a giant telescoping sum. And the reason I chose to write it in that expansive form is that it now contains 4 terms corresponding to the 4 things that we've been talking about. The structural disadvantage that preceded the algorithm, the bias from the choice of outcome, right, g instead of f, the bias from the choice of features, r of x instead of x, and the bias from my training procedure, t instead of h, right? And so in the sense that claims of discrimination or bias always inherently involve an attribution problem, right? Where did this bias get introduced? This is allowing us to decompose it into these components. And also is a kind of enumerative exercise, right? Often when we engage in an informal discussion of how algorithms introduce bias through the choice of features, the choice of outcome, through the training, it's completely fair to ask the question, is that everything? Maybe that's simply 3 out of 12 possible examples you could have thought of. And in some sufficiently abstract sense, it is everything because of this decomposition. Those 3 plus the initial structural disadvantage. Okay. So this is sort of the first level of argument that says, if we have the ability to audit algorithms, we can actually do something that's very hard to do with human beings, which is actually attribute where bias is coming from. But I wanted to move further into this question of, the interpretability of the algorithm, right? Our ability to analyze the algorithm. And in particular, talk about the role of simplification in that, right? What are the roles of simplifying the features and the objective function as part of this machine learning pipeline? And how's our ability to audit the algorithm come into that, okay? All right, so for that, I'm going to stay with the same model, and I'll show you an extended example where this plays out. So again, applicants described by feature vectors, and for simplicity, let's say they're Boolean feature vectors, productivity function, and I'm engaging in some kind of a screening process, right? Let's imagine hiring, or let's say graduate admissions, where I'm going to sort everybody by F value, and I'm going to admit the top R fraction. Okay, applicants can belong to either the advantage group A or the advantage group B. I have this, therefore, extended feature vector. And again, the function F does not care what group you belong to. Rather, the effect of group membership is that features conferring higher productivity are relatively more abundant than features conferring low productivity, right? So we'll have this likelihood ratio condition that I'll use, which says if X is a better feature vector than X prime, right, because it has a higher value of F, it's relatively more abundant in group A than in group D. All right, so that's the model. Let's ask what happens as we begin modifying the function, either to simplify it or to represent it somehow. And to do that, I'll pick an extremely concrete example so that we can all kind of work through it in our heads. Obviously, this is simpler than any imaginable example that we'd see in practice, but at least we can do this one by hand. Imagine I have 2 Boolean variables, x1, x2, and the true criterion is the conjunction of x1, x2. And so I can represent the entire thing in this truth table, x1, x2, group membership, and F. And let's imagine the frequencies of these vectors are as follows. Group A and group D are both half the population. If you're in group A, then each variable is set equal to 1 with probability 2/3. And if you're in group D, each variable is set independently to 1 with probability only 1/3. That's the sense in which group A is advantaged. Okay, so these are the frequencies of each combination of feature vectors and group membership in the population. So if we work this out, it says that at all small admission rates, right? If I admit up to, say, 5/18 of the population, which is how many people have F equal to 1, then everybody I admit has F value 1. So I'm basically doing perfect screening. And if I'm pulling basically indistinguishably from that group, right? I have some process that just keeps feeding me people with F of X equal to 1. A 1/5 fraction of that group will be from group D. Okay, so group D is underrepresented because of the disadvantage. Okay, so now suppose we start simplifying the function F, which we might do for a variety of reasons, right? Right, so imagine we only collect x1. Maybe that's because collecting x2 is too expensive. Maybe it's for reasons of interpretability, right? In a more complicated function than this, I might drop some of the variables, which is a standard strategy for how to enforce interpretability on a rule. Maybe I'm doing it for out-of-sample generalization, right? Rules that depend on fewer variables are effectively regularized and might generalize better. Okay, so in this example, we could imagine we're doing graduate admissions. X1 is grades. In this extremely stylized example, X2 is the quality of undergrad research that somebody did. It's very cheap to look at grades. It's expensive to look at someone's paper and actually evaluate it. So I'll just keep X1 and just evaluate based on that. Well, if I do that, then I go from the truth table on the right, which has 8 lines, to the truth table on the left, where I've collapsed everything down to just 2 rows. The row where X1 is equal to 1 and the row where X1 is equal to 0. and the way I do this is I just look at applicants, I put them into the row they belong in, and I admit in decreasing order of estimated F. Now, estimated F is not as good as F, right? Because what'll happen is that for all small admission rates, I'll pull from the top row, and I'll just pull essentially an indistinguishable sample from it. So the average F value of the people I'm getting is now 5/9, not 1. On the other hand, 1/3 of the top row is from group D. So the fraction of group D is now 1/3 rather than 1/5. So relative to the true F, my simplification has produced gains in equity, so larger fraction of group D, losses in efficiency. And that's a trade-off that we often see when people talk about fairness and bias in algorithms, that I modify the rule, I reduce efficiency, I increase equity. But we want to argue here that actually that trade-off hides a lot of more subtle things that are actually going on. And it's also, in a sense, a false trade-off, since it's, as I'll argue in a little bit, never the best thing you can actually do in this situation. Okay, so here are the sort of more subtle points I would like to make, staying within this example. The first one is, if you were to take the original 8-line truth table over here on the right, and you told me x1 and x2, and you asked me, would you also like to know the value of their group membership D, right? And you're someone who's just interested in maximizing F. Your goal is to just maximize F. If I ask, would you like to know the group membership, A or D, you'd say no. If I know x1, x2, I have everything I need to know to make the decision about F. I don't care what group they come from. Now, suppose I go over to the one on the left, and I say, I'm telling you x1, and that's it. Would you also like to know the value of group membership? Then unfortunately, you now say, yes. In fact, I would find it useful to know the value of group membership, because if you told me not just x1, but the group membership, I would build this new 4-line truth table in which x1 equal 1 and group membership equal to A comes first, and that has an average F value of 2/3. Second comes x1 equals 1, group membership D, that only has 1/3. Right? If I admit in that order, then for small admission rates, I'm actually getting a higher average value of F. But I've done it in a way that's hurting group D. So what's happened? Effectively, this simplified rule on the right, this 2-line truth table, simplification has transformed disadvantage into bias. Right? With the original function, we had disadvantage, but we didn't have bias. We didn't have decision makers incentivized to discriminate against one group. As soon as I simplified, now suddenly decision makers have a newfound incentive that didn't exist before. They actually want to seek out values of group membership, and in a way that hurts the disadvantaged group. And what's interesting is how this simple model is actually recreating something that we recognize from the behavioral science literature, in which the argument, and this is a robust argument that's played out in many, many empirical contexts, when people are in situations where they're making decisions under conditions of low information or rapid decision making, is when they're particularly liable to fall back on negative stereotypes, and in a way that particularly hurts disadvantaged groups. And that's effectively what's happening here. Because I simplified this truth table, the algorithm, this very simple algorithm, wants to seek out group membership in order to do this. What's intriguing here is that there are policy implications of this also. In the past few years, people have, empirical social scientists have evaluated policies that say, for example, there are certain questions that you are not allowed to ask on job applications because they're associated with disadvantage. And what people found actually through randomized control trials was that if you look at situations where those policies get introduced, you often see aggregate discrimination increasing, right? With the hypothesized mechanism being that when employers are not allowed to ask certain questions, it increases the chance that they begin to consciously or unconsciously fall back on stereotypes that they have to fill in what they feel to be sort of unconsciously the missing answers to these. We think of this all as an extremely human thing to be doing. But in a sense, it's not just that. Even an 8-line truth table will start to seek out protected attributes if you take away information from it and then ask it to maximize F, right? And that's effectively what's going on. There's a second point here, though, also, which is that this idea that simplification was a trade-off between efficiency and equity is sort of an illusion, in that it's never the optimal trade-off. It's never the best trade-off you can make between efficiency and equity. So let me show you one other example. Suppose, again, I gave you this 2-line truth table where I put x1 above x0 and you admit in this order. There's a change I could make to that truth table that would simultaneously improve both efficiency and equity. What I could do is I could sculpt out of the first row a cell from it, which says, if x1 equals x2 equals 1, and the group membership is D, rank that group first. That group has F value equal to 1. So if you admit in this order, according to this 3-line truth table, you'll admit row 1 first. You'll do better on F, and you'll certainly do better on equity because you're admitting members of group D, right? So essentially, it's a Pareto improvement in the language of mathematical economics that I've simultaneously improved on both efficiency and equity, right? The simplification by just eliminating variables was not the best trade-off between these two things. Now, you could ask, is this just a mathematical construction, or do I recognize this in everyday life? And I would argue, most people who've been involved in graduate programs recognize this truth table transformation, right? This morph that we did from things that we do, right? We might say as a graduate admissions committee, we are not getting enough people in our admitted classes from Group D. Let's create an internship program for members of Group D where they come and do research with us. And some of them do incredibly good research. And we then know that when we go to do Ph.D. admissions. What have we done? We've effectively said we're going to invest cost in collecting the value of X2, right, the quality of research, for Group D. And the people who do extremely well are now, that factors into the decision. In the process, you've now increased the fraction from Group D in your pool, and you're actually doing better on the quality of applicants. And that's the Pareto improvement that we again see sort of emerge here. So what it says is that in the kind of landscape of all possible simplifications of this Boolean function f, right, as we walk around on this landscape of truth tables, the act of simplification gets us to this interesting unstable point in the landscape. In one direction, we tilt into incentivized bias, causing algorithms to want to seek out the value of the protected variable so as to improve the value of f. And in another direction, we can move toward Pareto improvement, where we can actually simultaneously improve efficiency and equity by doing a modification to the truth table. Now, everything I've said here has been carried out in the context of this extremely simple example. But the basic results that we're able to show is actually that what holds in this example holds in general for every Boolean function. Okay, so the theorem is that for every Boolean function f that takes real valued outputs, that's the productivity, satisfying the disadvantage condition, and a genericity assumption that essentially says the values of f are in some kind of general position. And for every way of simplifying f to a function g, which consists of collapsing rows and using average values in those rows, like I was doing, two things must hold. And they're basically the 2 points that I've been making. One is the Pareto improvement point. There's always an approximation to f that strictly improves on my simplification g in both efficiency and equity simultaneously. And two, if g, my simplification, does not use group membership, then adding group membership to g as a variable increases efficiency and reduces equity. And that's the dangerous point in point B, because for an agent that just wants to maximize f, if adding group membership increases efficiency, then there's an incentive to seek out group membership. And it's a pernicious incentive because using it would actually reduce equity. Okay, and so what holds in our example holds for arbitrary Boolean functions, although with a much more complicated analysis where we actually have to deal with a number of things that come up, including Simpson's paradox from statistics and a number of other considerations that make this relatively hard to do for arbitrary functions. Okay, so with that, I want to wrap up just with some final thoughts. Our analysis of the machine learning pipeline, the attribution of bias and discrimination across it, leads us ultimately to consider the effect of simplification and how it interacts with disparate impact. And the argument is that simplification of a function, while sometimes obviously necessary because it's impossible to collect all the relevant data or use the full function, we nonetheless have to watch out for two things. One, that it creates an incentive to use group membership in a way that hurts Group D. But two, that it creates opportunities, right? That a simplified function can often be productively unsimplified in a controlled way to strictly improve both efficiency and equity. It also feels like the tip of an iceberg of many, many questions that we could ask here, right? Other formulations of simplicity, right? I've been talking about collapsing out variables, but there are many other kinds of simplification that we work with, and sort of studying the space of all these simplifications. But I think more broadly, what the argument has been is that if we want to think about algorithmic bias, we have to start by really deeply embedding ourselves in an understanding of human bias, right? Where human bias comes from, because that ultimately provides the data that these systems are built on and the foundation for the bias that makes its way into algorithms. And once we use algorithms, it allows us a new level of kind of concrete, explicit discussion about what are our features, what are our objective functions, how do we arrive at our decision rule, a kind of analysis of decision rules that really was never possible given the constraints of human psychology when it was just humans making the decisions. And I think what's exciting about the opportunity here is that many fields play a role in setting these priorities. And so, very much in the spirit of the ways in which data science represents a coming together of disciplines, I think these concerns about fairness and bias in algorithms represents a similar coming together in which technical fields like computing, applied math, operations research, and statistics can work together with the social and behavioral sciences, law, and policy to arrive at an understanding of some of these issues. And I think that's a very interesting conversation that all of us can play a part in going forward. Thanks very much.
Thank you, Jon, for a great talk. And let me just ask those who want to ask questions to Jon, please use the chat to ask your questions. So a question that I have, I think that much of this analysis is looking at machine learning. Does the same hold true if we're looking at general algorithms for decision making?
Yeah, that's a very nice question. So I think what's been interesting, and it's a case of almost sort of backfilling some of the history as the topic of fairness and machine learning sort of emerges, is to go back to periods like the 1970s and 80s where the sort of use of really industrial strength operations research techniques, integer programming for operations, began to get used, and you had an interesting sort of similar pair of considerations, right? One, that these methods were extremely complex and uninterpretable, right? It arrives at an optimum that humans don't necessarily understand, right? So we can run our airline at a level of efficiency that humans could never do. And two, that therefore biases could be making their way into these systems. And so I think some of what I've been talking about here sort of is similar in that the move to those kinds of systems created a certain explicitness about what are the relevant variables, what are the relevant objective functions that cause some of these conversations to happen. And similarly, that the sort of ability to attribute what was happening to different parts of the optimization pipeline. So I think there's a nice opportunity to really say, parallel to the machine learning pipeline is a kind of optimization pipeline, and I think very similar questions come up.
Good. So how do you see this transitioning to the real world? I mean, it's very interesting and fascinating to be able to explain where bias enters into these decision-making processes. But do you see a pathway for the tech transfer and who will be adopters of this?
Yeah, it's a great question. I think we see that underway already, and and I think there's there's both an opportunity here and there's sort of signs of danger we have to watch out for. That there was a first wave where it's part of the power of machine learning is anytime you give me a bunch of XY pairs, I can just build a black box that predicts new values of Y from new values of X, and so it's so easy to just start using that I think you had situations where local governments, for example, needed to predict something, and so they they paid somebody to give them a tool. That tool was often some handcrafted thing. It was opaque, and I think it took a while to have the realization that open source versions of this, where we can actually inspect the algorithm, where we can actually inspect the data that was used, can have equal or greater power. And so you saw the second wave where jurisdictions began to create advisory boards, for example, right? Who people coming from law and policy as well from technical domains. And New York City is the example I know best, which created a sequence of these advisory boards that would try to look at the use of algorithms in different parts of the city's operations and try auditing them for possible ways in which bias could make its way in. And so I think this is very much when people talk about these systems should be deployed with the involvement of many different stakeholders, creating organizations that actually bring together these perspectives. Now, simply because you've brought people together doesn't mean that's going to function effectively, but I think that's an important first step that that we need. And so I think that's one way at the level of both local and national government and the advice that they're getting. A second one is going to be companies, right? So the way in which Facebook ranks newsfeed, the way in which Google ranks search results, the way in which ads get deployed, all of these are going to involve, a lot of, I think the necessity of of oversight, even though these platforms are obviously, extremely technically adept to sort of have advice coming in there too.
So there's a question from Professor Julie Ansis, who directs NJIT's cyber psychology program. And she asks, first, thank you for the talk. Could you please provide takeaways for human beings to help minimize bias in decision-making situations, such as hiring, criminal justice decisions, promotions, etc.? That is, suggestions for individuals involved in that decision-making.
Yeah. Yeah, so that's a great question. I mean, I think there's sort of possible takeaways at two levels. One is, what can we learn from this as human users of algorithms, right? And I think part of this is if you're someone using a data analysis tool in your work to, help people who are sort of not builders of machine learning algorithms on their own to become, skeptical consumers of them. Because I think people have increasingly made the point that some of this comes down to a procurement question. In the end, we would like to use a data analysis tool. And somewhere in that process, somebody, say in local government, gets assigned the task of, procuring a tool for this. And often that's not done with the same care that other procurement processes are being done, right? If I'm procuring things that have a safety critical dimension to them, I have ways of making sure they meet certain quality standards. And given the newness of this area, there just aren't the same level of questions always being asked. And so I think that's one as consumers of the, but there's another one, which I'm sure the question is getting at, which is, what can we as human decision makers learn from watching what algorithms are doing? And I think, certainly one recurring thing that we see, and this is sort of, I as a computer scientist am sort of here leaning on the expertise of my co-authors from the behavioral sciences, that, when we're thinking about the risk of bias in decision making, one thing that often, one piece of advice that's often given is to be very explicit in writing down in advance of the decision, in advance of the instances you're deciding on, the factors you're going to consider, how you're going to prioritize those factors, and what your criteria are, what it is that you're evaluating based on. And to the extent that you can write those down in a rigid sort of way, it basically takes away freedom that you have at the moment of the decision, and it's that freedom that often ends up being a sort of giant doorway through which bias comes in. And so, and I think what's interesting about the role of algorithms in that is that if we think about, be explicit about the factors you're considering, write down a checklist, write down your process, right? The sort of limit of that is an algorithm, right? That's, if you could do that with perfect fidelity, it would be you executing an algorithm, and there are a lot of reasons why that's not, going all the way to that is not the answer, because there's a lot in your head that we can't elicit into checklist form. But effectively, I think this idea that we're going to try to cut down some of the freedom of action that we have by which bias comes in is a sort of step on the way toward algorithms, and some of the reason why we feel like, algorithms provide opportunities on their own.
So thank you again. This was just a thought-provoking talk and a new way of looking at algorithms and reducing the bias that we see, or at least explaining it and trying to have more fairness, as I think this is a very important topic, especially with machine learning and AI making a lot of decisions in these very important systems. So thank you again, Jon, for a great talk.
Thanks very much for having me, and thanks for these interesting questions.